But what I would do is I would start out all the way and then I had better and wanted like a fraction or vice versa. And I was like, I know, it was so mad.
Alright, exam is over. Oh, should we talk about how to check your grades? Yeah, let's talk about that. In case you still don't know, the grades are basically... What's new in this section? We are still considering functions, dealing with functions. However, this time on this section we'll focus on their graphs. What kind of properties their graph shows. The first thing we're going to take a look at is symmetries. In real life, symmetries are actually everywhere, like this flamingo on the lake. Its reflection or its image on the lake is upside down, right? If you draw a line here, it's kind of same flamingo. It shows up here like double but upside down. This is called x-axis symmetry if you consider this line x-axis. Okay? Well, everybody's face assumed to be symmetric, and you put a line right through your nose to your head, okay? But that's actually not correct. I think I've read somewhere your eyes can be a little further apart. I don't know. There's something like that. But more or less, when you look at people, you have one eye on the right, one eye on the left, one ear on the right, one ear on the left, right? Okay, this is y-axis symmetry. And round shapes, if you put the center of the shape right on the origin, they are symmetric with respect to this origin. What do I mean by with respect to origin? When you pick any point on that shape, connect it to the origin, and measure how much distance you went from all the way from this point to the center. And if you go the same distance to the opposite, same direction to the opposite side, you must still hit a point on that shape. Okay? If you are getting this for every point you choose, no matter what side you pick, then it's called symmetric with respect to origin. Usually, round circular shapes are automatically symmetric, but there are non-round other shapes as well. Okay? So 3 types of symmetries. X-axis, Y, and origin. Origin feels like kind of both X and Y symmetries, but that's not technically correct. Okay? Question is, once I'm given a question like this, do you see the graph? Do you see graph anywhere? No. How do I see the symmetry? I can't see. How do I test the symmetry without seeing the picture of this thing? Because if I see the picture, it's easy. Now I don't see the picture. How do I test what kind of symmetry, X, Y, or origin symmetry do we have? Is through this test. It's a little wordy, but read it. Read it. This is how you test y-axis symmetry. You always consider the opposite variable. Look, for y-axis, y is the letter. We are switching every x by minus x. Make all x's disappear, bring back minus x, and compare the new resulting equation to the original equation. See the old equation and the new one you got? If they still match the same thing, mathematically the same thing, then we call it, this picture or this graph has y-axis symmetry. For x-axis symmetry, look, the word has x in it. Guess what you're replacing with? You're replacing y by negative y. Every y should be made negative y, and you will get a brand new equation and see if it is still equivalent to the original one. For origin, however, for y we do x, for x we do y. For origin, guess what? We do both x and y. Both x and y will be replaced by minus x and minus y, and we will check if you still have the same old equation. Probably not. Okay? Alright. Let's go for our first problem. We need to do all these three. Unfortunately, it's a lengthy operation. We need to do all the three tests for the same equation. Well, after the first couple, you can do this under a couple minutes, okay? So you'll get faster. Alright, so I will first test X symmetry. We started with X, right? No, we started with Y. I will test it for Y first. Y-axis symmetry. Take a line and do it here. What do I do for y-axis symmetry? We replace who with what? X with negative x. So take this equation, make every x go away. Look, I will make x go away. What happened? Here is where x was, it's gone. And what do I bring back? Minus x. So I will put minus x in there. However, it was a single x gone. Now it came back with a minus. You need to put it in a parenthesis because you brought back two items under the same square. It's not single anymore. I will use a parenthesis. And compare this. This is new now, brand new. New. Compare the new one to old one. What is the old one? This is the old one. And tell me if these two are the same. Now, if I ask this to a first grader, they will say, no, are you dumb? Because this has a minus. But you're not in first grade. I'm asking, are they the same mathematically? Are they equivalent mathematically? I mean, when you operate on this, can you reach to this answer?
Yes.
Answer is yes, because when I multiply minus x times minus x, that's what square means, right? Square means double whatever you have on the base. Minuses make plus. Although they appear different, they ended up being the same if I compute through the process and compute these things. Same. If new equation and the old one matches, once you do this flip, what is the verdict? Conclusion is, what did you test? Y-axis, right? What do you say about y-axis symmetry? We do have, the graph has y-axis symmetry, yes. Okay? Can it also have x-axis symmetry? Maybe. You need to test it. Let's do x-axis symmetry. For x-axis, guess what do I replace? I replace y by minus y, agree? But where are the y values? Here, there is only a single y. I'm going to make that minus y, right? So again, yeah, this is old one. Old y equals x squared plus 5. I change this by minus y. Okay? And everything else is the same. This is new now. Did I get it right? Okay, what do you think? This is the new equation. New. And here is the old one. Compare these. Are they the same?
No.
Can you make them, they are not the same initially, but can you operate on this side or that one? Can you make them equal? I have an idea. This has a plus, nothing. That means it's plus. This is a minus, plus, minus. If I can get rid of this minus, they will match, right? So why don't we multiply both sides with a negative? Multiply both sides with a negative 1. -1 on this side. This is gonna flip to positive, isn't it? This is gonna flip to positive y. And we will get it done, right? Is that so? No, if I multiply the right side by -1, this guy and this guy, unfortunately, while you are fixing these sides, yeah, they are matching. What happened to the other sides? No match. Right? No match. So once I'm trying to fix the left side, the balance on the right side is broken. Once I try to fix the right side, the left side won't match. And I have a feeling these will never match, right? So after a while you quit. You try checking and multiplying. They won't match. They are not the same. So no x-axis symmetry. Okay? Alright, usually you only have one type of symmetry. The other two are never gonna happen, but I just want to do the job and test the last one. How about the third case? Origin symmetry. So in origin symmetry, we flip axis by minus x and y by minus y. Maybe it works this time. So I'm going to take that y and put it as minus y, and the rest square and 5 the same, and I will flip x by minus x in parentheses. Huh. This is the new equation now. What's the old one? This. Are they the same? Can you make them the same? I think we can. Can we multiply both sides of this minus 1? And they cancel. Y equals, these two cancel, right? Yeah, it's a match. Genius.
-5 instead of +5.
Yeah, I have actually butchered all laws of math here. I mean, yeah, you can multiply both sides by a negative sign, -1. These won't multiply because this is inside a prison of square. So they won't combine until you square this. Wrong. And besides, you need to multiply this guy as well if you multiply, right? And this is going to be minus. So they won't match, no match. So I can't get rid of those negative signs peacefully. So there is no origin symmetry. No, it was yes for this one, and no for this one. Okay? Was it the other way? That's right, correct? Okay. Alright, the graph of the equation is symmetric with respect to x. What did I do?
It was with y.
Oh, it was y, right? So this is what happens if you rush. Anyways, is symmetric with respect to y? Yeah. Is not symmetric with respect to origin. At least I got partial credit. Alright, next. Alright, what do you think about this one? You can kind of have a feeling. Square was around x here, and you got y symmetry, no x, no origin. This has the square around y. Guess which symmetry you will have here? You will have x symmetry. But I still want to show that quickly. It's pretty much the same work. So I will just do the x symmetry and be done with it, okay? You can test the y and origin and you will get nothing. So x symmetry I need to replace y values by minus y. Oh, how great is that? Y has a square. It has a square. That means if this minus y comes here, that minus is going to be wiped out because the square takes care of minuses. And new equation, old equation, match, and voila, we have x-axis symmetry. No y, no origin, because it's pretty much the same work we've done previously. Okay? Next. How about now? What is the difference? Y still have a square and a number, and this time x as well has a square. Yeah, anyone?
Origin.
It has origin symmetry.
Oh, it's gonna be yes.
Yeah, it has x-axis, y-axis, and origin, all of them. All kind of symmetries here. Maybe not. Yes, it is, yeah. Right? No? Anyone says no? Yeah, it has. Yeah. Look. X-axis symmetry. You need to flip y's with, I'm just doing this quickly, y with minus y. Question is, can I get back to the original y when I square this? This minus is going to be taken care of, and it's going to be plus y squared, 3x squared, so x-axis is yes. It's a match, right? Match. Y-axis, same way. Flip axis by minus x. Minus x squared is 3 plus y squared now. Well, this is the same as positive x squared. Match. Good. Since x and y-axis y-axis symmetry both happened, then we can automatically say it has origin symmetry without any test. But if you are interested in seeing that literally, just replace x's by minus x. 3 is still 3. And y by minus y. And you see this is back to original equation. Right? Anybody has an issue with understanding my steps? I'm kind of fast because, yes?
So if it has an origin symmetry, it has to have x and y symmetry?
No, we can't say backwards. Hold on. If it has both x and y axis symmetry, then it automatically has origin. But backwards is not correct. Just once, if it has an origin symmetry, some graphs have origin symmetry, but they don't have neither x nor y axis symmetry. Okay? Such as this one. What is this graph? Name of this graph is y equals x. Does this have x-axis symmetry? X-axis symmetry means you flip down and you get the same picture. Do you see it? Same picture above underneath this? No, it has no x-axis symmetry. How about y-axis symmetry? When you flip this to this side, you need to get this image on the other side already present, but I don't have it. This graph has no x-axis symmetry, has no y-axis symmetry, but it does have origin symmetry. Whenever I take a point, hit origin in a straight line, I go the same distance and can find another point on the other side. It has origin symmetry, okay? Or this graph as well. What's the equation of this graph? This is equal to x cubed, y equals x cubed. It has origin symmetry, but it has no x-axis or y-axis symmetry. Okay? Alright? So, number 3, this is all kind of symmetries. Is. Okay? Alright. Any questions so far? Now, when symmetries happen to functions, it's something great. We call such functions by special names, so we kind of honor them because of showing such a good property. We call them either even or odd function depending on what kind of symmetry they show. For example, if a function shows y-axis symmetry, we call it, y-axis symmetry is called even function. So you sketch a graph of that function, and if you see y-axis symmetry, oh, this is an even function. Perfect. But if a function is symmetric with respect to origin, a function is symmetric with respect to origin, such as these two, this one, y equal x and x cubed, they are both odd functions. They are odd. Okay? Alright, I have a question here. If a function shows y-axis symmetry, we named it, give him a title of even function. If a function shows origin, we give him a title, call him odd. What happens if function shows x-axis symmetry? I think they missed it. So this is a great day we can make our own title. We found something new in math. If a function shows x-axis symmetry, I will call him Adam function or Austin function. You name it, right? Why did they missed it? I don't think they're that stupid. They forgot to name x-axis symmetry for a function. Why?
So function can't have two domains, the domain is the same. So we have an x
Okay.
symmetry isn't going to repeat.
I think I got it. What do you mean? So let me give you a x-axis symmetry. This is a function. This is root x, correct? But to call this x-axis symmetry, I need to have, when I flip this across x-axis, I need to have the bottom part, bottom image as a part of this function. So this is now x-axis symmetry. This used to be root x, but when I combine these two together, I cannot call it root x anymore. It's something else. But the question is this a function? Those titles are reserved for functions. But this is not a function. Why? It's something called, what is this called? We've done this in chapter 2. What is this called? Vertical line test. Just because you have a graph doesn't mean it belongs to a function. Like I can put a picture of a monkey here. It's not a function graph. Function graphs should be always intersected once by a vertical line. So this is no longer a function. It has x-axis symmetry, but it's not a function. As a matter of fact, anything having an x-axis symmetry cannot be a function. So that's why they didn't have a name for x-axis symmetry as a function, because it's impossible to happen for a function. Okay? So you have only two types: even, odd, y-axis, and origin symmetries. Question number 4. What kind of symmetry do you have here? And what kind of function then? You need to check for y-axis symmetry and origin symmetry. Anyone?
Y-axis
It has y-axis symmetry. How do we check y-axis symmetry? When you pick a point, any point on this curve. Okay, I'm blindfoldedly picking a point. Here, okay. You need to go hit the y-axis vertically, horizontally actually, and go the same distance, measure this distance with a ruler, and go the same distance to the other side. The point you obtain, these are the same distance. The new point you obtain should be on the curve. Is it on the curve? No. So it has no y-axis symmetry. It looks like symmetric, right? Same picture showing up on that side, same pictures. But technically, when you really measure things, it's not symmetric. It's not. How about this one? Is this symmetric? Look, $1, $2, $3, almost $3 boxes. 1, 2, almost 3 boxes is here. You are short. You are short, almost hitting, but no, not really. So it has no y-axis symmetry. So we cannot call this even. How about odd? Is it odd? Let's test this point for origin symmetry. How do I test it? Take a ruler and connect this dot to origin in a line. And measure this distance, okay, 1 corner, 2, almost 3, and go the same distance opposite side. 1, 2, and 3. I tested one point and it's on it, but I'm not convinced. I'm gonna test another one. Let's pick another one. How about this? I'm going 1, 2, almost 2 halfway, okay. And I'm going to go 1, 2, and a little bit more, and yeah. I took second point and it's on it. Let's take someone really far. How about this guy? Oh, we always pick from the top. Why don't we pick something below right here? Let's test this one. Now, eyeball this thing. Move. There. I think it's on it. So you really need a ruler though. Measure these things really good. Okay, I did 3 trials. I'm convinced. This has origin symmetry. Agree? Okay? So this is an odd function. Does it make sense? Do you want to take a 4th, 5th one? Yeah, you can do that. Oh. Question was this. Again, don't go trying all the time. It's just don't go with multiple choice options here, okay? Test it, get the right answer, and then choose the answer. Don't peek at the solutions or anything. What is this one? How about this one? Too much. You see it all once? Yeah. How about this one? What do you think?
Even.
Even. Even. All agree even? Let's test. When I pick a point from the right, I go the same distance. Do I hit something on the left? Yeah. How about this one? I travel 1, 2, 3 dots to the left. 1, 2, 3, another 3 dots. Do I hit something else? Yeah. This point? Yeah. This? Yep. It has y-axis symmetry. It's even. It's even. Can a function be both even and odd? No. It's only one choice. You can be neither even nor odd, but you can't be both at the same time. So I'm not gonna check the odd case. I mean, if you're interested, you can do it. You can pick one. This one needs to be here. It's missing. It's missing, it's not odd. So it's even. How about this? It's even, odd, okay? Neither? I have a feeling this is odd. Am I wrong? Look. This point, I go the same distance and hit it here. This point, we go hit there. I think it's odd. Am I right? Now I'm always picking the convenient ones, such as pick this one. Pick this one. And stop. I missed. I meant the same distance. Same distance. Other side. It's missing. This is not odd. Is it even though? It's easy. Check this point. Go to the same distance to the other side. Did we get this on the picture? No. Neither. You were right. Part C. What? Oh. Wait. Yeah, it's B for my question. Neither even nor odd.
Or was it not a function?
What? What's that?
Never mind.
It can be still a function. It can be still a function, but it's not y symmetry. It has no origin symmetry. It's still a function though. You see vertical line counts. Okay. Here is the problem now. No pictures given. Same statement. Look at the statement. They want us to decide this is even, odd, or neither. I think they've missed a big part. Where is the picture? No pictures. Well, this is the moment you need to decide whether it's even or odd by algebra, by definition described here, which I'm going to show next. How do we use the definition or algebra? How do you calculate odd or evenness? Okay? Alright. Here is the formal definition of evenness. You replace this axis by minus x, and it still should be, this is old equation. This is the new one. It's nothing different. We've done this. You replace all x's by minus x, get a new equation, and compare it to the old one. If they are matching, we call it y-axis symmetry, we call it even. However, you replace this x's by minus x, get a new equation, but it's not matching to old one, however, it's matching to the negative of the old one. This is negative of old equation, then it has origin symmetry. We haven't used this much in the past, so this is maybe new, okay? But here is what we need to do in any case. You need to compare f of x old equation, or in this case it's p of x. I want to change this to f of x to reduce any confusion. I'm going to take f of x, compare it to the what happens if I replace x's with minus x. So again, what is f of x? It's given right here. This is minus absolute x, 10 x to the 10th plus 7. This is given. No math required here. F of x is this thing. How about f of minus x? What happens if I replace x's by minus x? Let's do it. I'm going to take away all x's. Look, I took them away. All empty spots. I'm putting them back in with minus signs. When I'm putting back into the base of a power, don't miss the parentheses. You need a parentheses. I want you to compare. Are these two things equal? Old and new one. Are they matching? Or not matching? You have two choices. If it's not matching, we need to do something further. If they're matching, you stop. If these are matching, you stop and say, oh, this is an even function, and go to the next question. Are they the same?
Yes.
Who said that? Yes. They are the same. Why? Because absolute value of negative things is the same as absolute value of positive of them. So in other words, this minus is gone. Absolute value cancels negatives. Absolute value remove negative. Right? Isn't this true? Negative 3 is the same as just positive 3? Yeah, that's tough. Right? Negative 3 and positive 3 are both the same answer because this is 3 and this is 3. Kinda you can ignore the sign, negative signs under absolute value. So negative absolute x, absolute negative x, and absolute positive x, the same. So that part is taken care of. My question is, how about the minus here? How do I remove that minus in the second place to make them the same? How do you say this? What kind of power is this? It's an even power, even number. When you have an even power around a negative number, they always turn to positive. Okay? Negative stuff raised to even is always positive stuff with that even power. Okay? Got it? Because you're multiplying this minus itself this even many times. 10 times the minus itself is positive. But if this was 9 times, then it's a whole different picture. It's gonna be staying negative. If it's odd, it's negative though. Okay? Alright, so this question is resolved. These two things are equal. So we have the situation that when I compare them, they are equal. We go with even function here, all set. Okay? Okay? Question? Next. How about now? Can I call this f again? F of x versus f of minus x again. I think we have a little problem now. It's minus 6x to the 5th plus 2x cubed plus x. This is minus 6 minus x to the 5th plus 2 minus x cubed and minus x to the 1st. I wanted to show that last exponent because there is always one thing common in all these exponents. What is common in all exponents? A pattern. What is it? They are odd. Yes. Odd. 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 What happens if you have a negative base under an odd power? That negative comes out as negative. It won't disappear like 10th. 10th power to kill this negative, but this negative will survive from this odd power and come in front, actually all the way here. And it's gonna flip all these signs and that sign. So we have here positive 6x to the 5th minus 2x cubed minus x versus this. Now, who dares to call them equal? Are they equal? Are these things equal? Can I call them equal and say this is even and go home? No, they're not equal, obviously. Right? This is negative 6, positive 6, positive 2, negative 2, x minus x. If they're not equal, what are they then? Opposite. If all three signs are opposite of each other, the entire function on the right should be negative of the first one then. They are equal to opposite of this function. Like you have a minus in front. Once you multiply that minus, then yeah, they are equal. So f of minus x is opposite of the original. So what does this say? If you have this here happening that, what do we call it? What kind of function this is? It's a odd function because of opposite sign of the original. Alright, we have two more and then we can stop. No, we have actually one more. I lied. One more. What's the verdict here? Alright, you have 30 seconds to decide. You have 1 out of 3 chance. How many of you say this function is odd? Raise hand. Odd, raise hand. Nobody? Disappointed. Alright, how many of you say this function is even? Part C. Even. Even. You're scared now, right? Because you're running around. Nobody? How many of you guys say it's B? Neither. This is strange. My first initial response would be with Austin. I would call it even because these are even powers. They wipe off negative x's, right? Almost correct, except this little number right there stuck with my x. This number is messing up everything. You will see why. Why is it messing up? Alright, we're comparing f of x with minus f of x versus f of minus x, right? Let's substitute f of minus x everywhere. Minus x everywhere. Minus x squared 9 minus x minus 4 versus this guy is x squared 9 x minus 4 squared. Now, are they matching? Are they the same? Almost. This thing is positive, yes. This is gone. It's positive because of the square. So they match. Top match. How about the bottom? I have this extra negative, but can I wipe off this minus with this square? Can I? Yes, if you call that minus from 4 as well. So you need to make this. Take minus from both of these guys, and this turns to positive 4. Then this minus, once you square it, becomes positive. You have a match among x's, but this is minus 4, that's positive 4. This time 4 and minus 4 differs. There used to be minus x and positive x difference. You fixed x's, but you destroyed 4's. They are different now. So they will never come together. They will never match. You can see this also by foiling. If you like, foil this thing. And foil this thing. You will get 3 terms on the left, 3 terms on the right, multiplied by 9. They won't match. They are different. Okay? They won't be opposite either. If you put a minus in front of this here, they won't still match. So this is the case of the neither. All because of this guy. I wish this was gone. Then you could have canceled it, but because of that 4, it's not odd, it's neither even. Okay? Alright, when you come back, this is just the first half of this set. We will learn more, but no more pictures of graphs, even odd symmetries. We will take a look at 2 special functions. Okay?
Were you going to hold attendance for class review?
Yeah, right now please